Welcome everybody to Sustainable River Basin Management Module 4.2, Part 2. We are still talking about the modules towards sustainability in river basin management. And this time we will continue on river basin management function and planning specifically. Last time we have started talking about land use and water planning, and in this module I want to talk specifically about mapping of water protection areas. First of all, what is source water protection? Source water protection is very closely linked to soil protection, soil sciences. However, it goes beyond simple water pollution control and recharge. It is essentially a part of land and water use planning. In many countries, source water protection is conducted in the way of artificial recharge or water treatment before recharging artificially groundwater. But this is just one of the functions of source water protection. Now, why do we want to do source water protection in the first place? It is for the reason that contamination of water is often not detected until very late. The extent of pollution and pathways are often detected only with very great difficulty. Can be very resistant and very often irreversible. This one? Okay, I'm repeating. Let's talk about source water protection and why we want to deal with that. Very often contamination of water is not detected until very late. In many cases, it comes along with an extended pollution and pathways which are detected only with very great difficulty. Contamination may extend over very large areas and may be very resistant, and in many cases be irreversible, difficult to clean up. And for that reason, we opt for regional or aerial protection of the source waters. Now, we have been using source water protection, and the definition for source water protection area is that we are looking at a water body from which raw water is abstracted for human consumption. The term raw water means that it's an untreated water which still has to be treated to be safe for human consumption. Some countries require for a source water protection area a defined minimum rate of abstraction or a certain minimum number of people that should be served with drinking water, so that protection areas can be declared and are justifiable. It includes all types of abstractions of raw water, which means it includes surface water bodies, reservoirs, rivers, as well as subsurface water, groundwater. Now, how can we achieve something like source water protection? And this has been done through a holistic management approach, where we include all of the components of the water resources. This includes the catchment area, as well as the water, as well as the treatment plant and distribution system. When we talk about water, we mean rivers, the check dams, drinking water reservoirs, aquifers, all of the compartments accommodating, hosting water. Visualize, we are looking at an upper catchment area where some activities may take place, where we have rivers and tributaries. We may have human settlements, towns, villages, some industries, any sorts of land use, and we may have even sewage plants here. Then we usually may have in a lower catchment where we have maybe a drinking water reservoir, which will be before the water passes into the drinking water reservoir, It will pass through check dams where most of the silt and sediments will be deposited. And then from the drinking water reservoir, it will be abstracted and taken to a treatment plant. And from there, it enters a drinking water distribution system to reach the end users. Now, all this has to consider the interactions between water quality and quantity, both of the components, and are settled down in a so-called catchment management plan. Now, let's look into the source water protection and the components which should be specified in such a catchment management plan. There should be a clear understanding on minimizing the discharge of substances and organisms which may affect the quality of groundwater. Those could be hazardous substances, chemicals, for instance, but it could also include or should include organisms. It should prevent new potential threats to groundwater in the catchment areas. There should be measures which prevent adverse temperature changes of groundwater. And there should be a targeted monitoring of the groundwater resources for the public water supply. Now, let's look into how these source water protections take place in reality for surface water components, the reservoir protection. This is just an example of a water reservoir here, a large artificial lake. And we can see various land uses here, some villages. There's a bridge crossing this drinking water reservoir. We have agriculture taking place here. And then we have some infrastructure here related to the maintenance of the water reservoir and for water treatment as an abstraction point. Now, all of these drinking water reservoirs should be surrounded by a water protection area. What we can see also in this case, there's a green belt going around this reservoir here, which is specifically kept as a protection zone, the first protection zone. There is no specific size or distinct fixed size given for the extent of such buffer zones. They are usually defined on a case-by-case basis, depending on terrain, geomorphology, depending on the topography of a watershed. There are, however, some countries which have legal provisions for fixed buffer zone width, something of, for instance, 200 meters from the mean water level height, land inwards is a protected zone, or something similar, 200 meters, 100 meters. Some have half a kilometer as a buffer zone, but many also just keep this open and flexible as per terrain, topography and geomorphology. Now, how can this look like in a map or in a sheet of paper? We have here the different protection zones, 1, 2, and 3 divided into A and B. And we have zone 1 comprising the lake, which has the highest protection status. Only a dam operation or dam protection will be allowed. Then we have the second zone, which protects the inflowing waters against pollution that caused by direct discharges or erosion and runoff, and potentially being flushed into our reservoir. And we have zone 3, which includes the entire catchment area. So, and this means that land use restrictions and prohibitions may apply for activities which potentially threaten the water quality. So certain sizes of settlements may be restricted. Certain industries, agriculture, transportation may be restricted in the catchment area where such a water reservoir occurs. Now, the concept for groundwater protection is similar, but a little bit different. You will see why. This is an example map of such a zoning concept for groundwater protection, where this red dot here indicates the location of our borewell, the abstraction point, and then we have again a zone 1, zone 2 and a zone 3 to it. We have different land uses here and also infrastructure, roads, settlements and so on in those areas. Now, abstraction zone, the zone 1 corresponds to the abstraction point itself and the immediate area around it. The zone 2 and 3 will differ in shape. We will look into this now. And there will be different land use restrictions applicable as we move further away from the abstraction point. What we can see here is also that there is not a single shape which we apply to the size of the zoning. The zoning is basically depending on groundwater flow directions and on soil and aquifer properties. Let's look into this in detail. Now, we have our aquifer system here. We have a borewell sitting here, this blue symbol here, and then we have blue arrows indicating our flow directions, our groundwater flow direction, our recharge taking place in the various places. And as we start abstracting water, we are increasingly drawing water from the downstream areas of our groundwater flow direction. And accordingly, there will be zone 1, the area immediately around our borewell, and then we will have our zone 2 as the so-called inner protection zone, or more commonly used is the term 50-day limit. And we will have our zone 3 corresponding to the outer protection zone from the borewell and up to the limit of our catchment, our groundwater catchment area. So what we see that these zones extend upstream of our groundwater flow direction, and very much depend on how fast this water is moving from the infiltration point towards our abstraction. You can imagine that this is changed or influenced by the amount of water that has been taken, abstracted, pumped from such a borewell. Now, if you look at the scheme from the vertical position, we have our borewell here, and this inner abstraction zone will be fairly fixed and predictable. It will be just about 10 meters, 6 to 10 meters around the borewell in a regular shape to protect immediate return flows. And then we have our 50-day limit according to our abstraction rates and groundwater flow velocities. And then we have an outer protection zone which corresponds to the catchment boundary indicated by these arrows. Now, the zone 1, as I said, about 10 meters around the borewell, usually it's just 6 meters. It's usually fenced to block infringements and to avoid that people park next to the borewell or do their laundries next to the borewell and so on. And then there should usually be no land use changes allowed in the area. Important is that it's no land use changes. The zone 2 extends from zone 1 to the point at which groundwater will travel at least 50 days between recharge and abstraction. That 50-day limit comes that this is a minimum retention period to eliminate microbiological contamination, usually bacteria which will be infiltrating through the soil, moving through the soil layers towards an abstraction point will be dead within a period of 50 days. In some rare cases, this will not be efficient enough, and in such circumstances, a 200 days limit may be necessary. It also shall protect against deterioration such as recontamination, return flows, for instance, taking or repolluting water while it travels through our aquifer system to the abstraction point. There's a usual thumb rule of 100 to 200 meters of radius, whereas you have seen it's not a circle itself. It's following flow directions, but it can be calculated very precisely, calculating flow velocity from the hydraulic conductivity, the hydraulic gradient, and knowing the effective porosity of our aquifer. So there are parameters necessary about our water and about our aquifer system itself, which we can obtain from geological maps or from pumping tests conducted on our abstraction point or on abstraction points in the near vicinity. What is not allowed in zone 2, prohibited, is the use of any fertilizers or manure, any herbicides, pesticides and things like this, and any intervention that would change or interfere with the landscape. What we mean by this is that our landscape, as our water moves through the aquifer, it usually becomes cleaned. There's a cleaning effect and a filtering effect taking place. So that's why we want the ecosystem, the landscape, to be functioning to conduct exactly this role. Now, the zone 3 covers the area of zone 2 up to the catchment boundary, and this shall ensure the protection against far-reaching adverse effects, especially of not readily degradable chemical and radioactive contaminants, which would travel long distances and remain over long periods of time in our water bodies. We want to protect the landscape capacity, which will attenuate and remediate contamination and any effects on our groundwater. So hazardous substances shall be handled with very care or minimized. There should not be any new construction of industrial plants, oil storages or oil pipelines allowed within this zone. So there are several restrictions which may interfere with other human activities. So it's a question of priorities in this case again. Now, how can this work in an urban area? We know that many urban areas depend on groundwater entirely, and not all of the parameters of aquifer geophysical parameters are always available and known. And for that reason, there's a slight simplification used in urban areas. First of all, zone 3 is divided into 2 zones whenever the distance from the abstraction point to the subsurface divide is larger than 2 kilometers. And then we use a so-called isochronal concept, whereby the inner zone of zone 3 would be corresponding to a 1,000-day limit, which is the time for a water drop to infiltrate and move through the water body to our abstraction point, and the outer zone of zone 3 would be a 10-year limit. In that way, we can exclude large areas which would be maybe part of groundwater catchment zone and can remove them from the strict restrictions which are applicable to the zone 3 otherwise. So the justification for this is that it assumes that there's a functioning stormwater drainage in such urban areas, that there's a proper and functioning sewage and garbage management system, that most of the area is built up or paved and so to say sealed from unwanted and unsafe water infiltration, from water percolation. Examples of such groundwater protection, zoning and dependency of cities from groundwater are the cities of Berlin, Hamburg and Dresden, just examples from Germany, larger cities in Germany. And just to give you a feeling for that, the extent of such protection areas, 1/4 of the city area of Berlin is designated as water protection area. So it's very much visible and applied. Now, the suggestion for you before we conclude for today is you should find out if there's a legal provision for the discussed kind of source water protection available in your country. What are the challenges in the implementation of land and water management plans? How could those be overcome? And you should search, for example, zoning maps for source water protection. You could find them online. There are many countries who use that concept, and you can get examples, including reports about how these zoning maps were produced. With this, we close for today, and we see us next time again.